So this is
So
working, right?
it's a good thing we brought up differential equations before our next speaker, Paul, who has done a very impressive amount of work on scientific computing, and I'm thrilled to hear what he has to tell us today.
Thank you for your kind invitation and introduction. I'm very happy to be here. I'm actually probably not going to do what you wanted me to do. Bear with me. I want to try and, well, what I really want to do is we have the remarkable privilege that we're all in the same room thinking about common stuff. And rather than talk about stuff you could read in my research papers, I thought we'd try and do something to provoke actual live thinking and perhaps even talking to each other. So I'm going to talk about a huge pile of things. I'm going to do my best to leave time for questions and discussion. The huge pile of things is done by a huge number of people, a couple of whom are actually in the audience today, Tobias and Michael. This talk, well, I went to a really good workshop September last year, organized by a friend of mine, Didem Unat, with some colleagues of hers. And the focus of this workshop, it's been running for a few years, this was just the most recent one, was abstractions for data locality. And what I wanted to talk about today is sparsity from the context of locality. So my thinking is that actually what's hard or interesting about locality from an implementation point of view, what's interesting about sparsity from an implementation point of view is very much about sparsity. And I'll say, hopefully, I'll try and make that case as we go forward. So I've got lots of slides, not too many, but I'll have to hurry, but I might skip some because I don't really have to finish the talk. If we ignite a decent conversation before I finish, then my work here is done. All right, a little bit about where I'm coming from, and then we'll dive in. So I've done all kinds of different things in architectures and cache coherency protocols and lots of performance stuff and even some bounds checking. I'm particularly proud of some work we did on pointer analysis, which ended up being implemented in GCC. The best citations are not from other papers. They're from widely used open source code. I think it's fair to say that although we were very proud of it, the impact of static analysis for pointers is pretty limited. Basically, it's really, really hard. And I'll say a bit more about that in a moment. That led me to get frustrated and to think, well, hang on a minute, we talked to all these applications people and they know so much about how their code could be implemented efficiently. Let's think about how we could automate that. And that led me into the world of PDEs, which Gilbert mentioned. So we've built Firedrake. I'll say something more about that. DeVito, you heard a tiny bit about this from Tobias earlier, and PyFire is another. These are all tools that automatically generate the code starting from the equation itself, from the weak form of the PDE in the finite element case. You type in the symbolic maths. It automates the textbook derivation and generates the code to assemble a linear system or to iterate your time step in an explicit method. And the really fun thing about that is it connects you to people doing all kinds of wonderful applications. I've always get sucked into, I tried to pull off the same trick in computer vision with mixed success, but we did loads of other fun things. So I do lots of different things. Let me also introduce this with this idea. I don't know if you've ever heard of it. I do not claim that I invented this term. I heard it from somebody who denies that they said it. But this is the concept of the Turing tax. Okay, so Turing, famous for many good things. One of them was the idea of a universal computing machine, a machine which could do anything that any special purpose machine could do and could be programmed to do it. Part of a thought experiment, thinking about the limits of what could possibly be done, he thought, instead of thinking about all those different machines, we'll talk about one universal one. The Turing tax is the cost in energy, transistors, time, whatever, of running a program on a universal programmable machine versus building the super highly optimized ASIC or whatever it is that would maximally specialize in order to massively to optimize performance to the limit. The Turing tax is the difference. The job of computer architects, arguably, is to minimize the Turing tax. The one way to do that is to become an accelerator specialist. The other way is to try and build machines which are programmable, take you some of the way along that full specialization, but retain programmability. And we see a lot of that in accelerator architecture. So that's the Turing tax. Here's another thought. Compiling's like skiing. So you want to get to the top of the mountain and build an intermediate representation that captures everything that we can know about the computation that we want to do. And once we've got that representation, we can come down the mountain, we can choose the best possible pathway, we can have the most fun. Along the way, there are some ski lifts, right? There's some static analysis that might help us build that representation. And on a good day, they take us a good way up the mountain, and the higher you get, the more fun you have. Of course, in a sense, all of this is a kind of Turing tax in the same sort of sense. It's the price to pay for using a general purpose programming language, when you could have fed the system with a direct representation of the computation you wanted to do that would mean all this analysis wouldn't really be needed. Right? And again, you might wonder how real that is. It's clearly partially real, at least some of the time. Okay. So what we've been doing, for example, in particular with those PDE tools, is trying to build power tools. Instead of something which is good for pretty much anything, we have something which is good for a subset of those things, but massively more efficient when it's the right tool. And I would claim that we're reasonably successful in achieving productivity. We actually raise the level at which people are thinking about their problems. Performance, we automate the optimizations they would otherwise be implementing by hand. And because it's automated, we can automate multiple backends for different platforms. That's the plan. All right. The thing is that it's actually not really the performance that's the most important thing about tools like that. The really important thing is to support the users in making a decision, having invented a new way to model a physical phenomenon. You want them, instead of diving into how am I going to implement this, they code it up, they figure out their model was wrong, they do it again the same day, right? And once you get there, those people are navigating their expertise, right? They are thinking about how to model their physics, for example. And you are taking it from here in terms of building a high-performance implementation good enough that they don't have to be thinking about it. All right, so the point of this picture is if you were exploring a country like Denmark, wouldn't it be great to have an incredibly fast car so that you could see as much of the country as possible? Wouldn't it be wiser to have a guide who tells you what you should actually do? And that domain knowledge is going to transform the experience on holiday. All right. So I was introduced as somebody who'd worked on tools for PDEs. Here's the compiler architecture for one of them. This is Firedrake. Firedrake automates the finite element method. So it implements a domain-specific language. I wonder if you can see my pointer, which goes by the name of the Unified Form Language. It's embedded in Python. We didn't invent it, incidentally. It was invented by the Phoenix people in Simula. So this is a kind of re-implementation of the same language. That language essentially invites you to type in your PDE, specify discretization. And what the compiler is doing is weaving those things together to generate the code that assembles the matrix, the linear system that you need to solve, for example, or enables you to solve it by constructing a matrix-free implementation. So this compiler architecture has been the subject of quite a lot of iterated design. And another thing you might think about is this is a sparsity workshop, where's the sparsity here? So there's a tensor contraction layer there. Now, mostly that's pretty dense, but in fact, sometimes it has interesting structured sparsity and block structured sparsity. That's a computation which is happening at every element of the mesh, like every tetrahedron of the mesh. The mesh itself, of course, is a graph or something, which you can also think of as a sparse representation in some sense. Of course, what we're assembling is a linear system, which is, again, a sparse matrix, whose structure came from the mesh itself. So I could talk to you about all the applications and so on. That's probably not the point. Oh, one little thing. Yes, this. We heard a little bit about how much we love rewriting. And there's a colourful history of rewriting behind this project, but one little bit of rewriting that I thought was really instructive was we did some work I was really, really pleased with on eliminating redundancies, redundant recalculation of things, generalizing loop invariant code motion. And we did it on a loop tree representation down at the bottom here. We later came along, and for somewhat different reasons, it created this tensor contraction layer up here. Then we realized that the loop invariant code motions that we were doing here were in fact factorizations in the tensor contraction representation. And that enabled us to delete thousands of lines of horrible tree manipulation code and replace it with a couple of pages of Python up here that just implements that factorization. And that's what winning looks like, right? That's the art of compiler architecture, is finding the right representation to make a hard problem an easy one. Right. Okay, this talk is actually not really about that. I'm sorry to disappoint you, Gilbert. I wanted to focus on this locality thing, right? What I think, and you might dispute this, what I think makes sparsity challenging is basically locality in its various forms. And what makes locality hard, well, maybe it's just hard, but something that certainly makes it harder is composition, right? When we compose constituent parts, we need to know where our data is, and we need to try and align our iterations and so on. And where I'm really going with this is that the key topic that underpins getting that right is the metadata question. How do I know where my data is? How do I know where my non-zeros are? How do I know how my data is distributed? And in dense systems, that's relatively straightforward, right? We take our grid, for example, and we can just divide it up. And that geometry is a small representation of where our data is. It's a compact representation. In the sparse case, or even simply the unstructured mesh case, you need something much bigger. You need something whose size, the size of the metadata, is somehow proportional to the size of the data itself. And that's trouble. Right? So the game in thinking about how to optimize locality is to try to live with or overcome that problem. Okay, so I mentioned locality, and the textbook tells you there's spatial locality, there's temporal locality. I've added physical locality, and you can argue whether it belongs here or not. But if we've distributed our computation across a parallel machine, then we need to think about where the communication is going to take place. What do we know about how to optimize these things? Well, spatial locality, roughly what we want to do is to co-optimize the layout and the schedule. We want to be accessing the data in the order in which it's laid out in our memory. And that's, well, it's easy when it's easy, and it's hard when things are more rich, when the data structures are richer, the sparsity, particularly with dynamism, this becomes more difficult. Temporal, so the big thing that we know, the story we know for what to do about temporal locality is tiling, right? And classically, tiles are rectangles, right? Tiles are rectangles, and that's a lovely compact representation of how you've partitioned your schedule, in fact. in order to achieve temporal locality. In the unstructured case, we divide our world into patches, but the patches have complicated shapes. And what iterations are in a patch, well, we list them, right? So we again end up with metadata in proportion to the amount of work we're going to do when we visit this patch. And again, that's trouble, right? So we've built that one. When we think about the communication optimization, we also run into problems. For example, if you have a parallel computation here and another parallel computation here, you might think that's great, everything's parallel, we're all good, until we realize that we have a all-to-all communication pattern between them, and we should have tried to optimize across that boundary in a way to minimize that data movement. All right. I'm worried I'm going to run out of time, and this is a monster slide. Should we do this one? A little bit, yeah. So I'm interested in the shape of the data and the shape of the computation graph, and when we get to know these things and how that affects our choices in what we're doing. So in the kind of classical structured mesh, like finite difference stencils, we just know, and we heard about DeVito that does that. In an unstructured mesh computation, like Firedrake, for example, and many others, of course, typically the mesh is not known until you start the computation and load the mesh into memory, but then you do know, right? You do some partitioning, you might do some renumbering, and optimize for parallelism, locality, communication, spatial and temporal, and then you can stick with it, right? You don't need to change any of that. You can run perhaps thousands of time steps on that partitioned and distributed and renumbered mesh. Of course, sometimes you're in this space where you do things like adaptive mesh refinement, and this messes you up again, right? And again, this is where you really start thinking, well, how big is my description of where the data is and what the dependencies are? And how can I amortize the cost of computing on that description? So one way to do this is to think about everything block-wise. That amortizes one way. The other is to do it element-wise, but to reuse that schedule many times. Finally, of course, we get into this crazy world where we have things like particles that move every time step. So the interaction graph of our computation, this happens in molecular dynamics, for example, is changing all the time. And so in our vision applications, we have similar things where as with each successive frame from the camera, you add observations to your graph representing what you know about the world. And you're optimizing that graph to try and establish the most likely configuration of things in your world. And each time you add some more edges, you need to re-optimize. Another lovely example comes from our work on pointer analysis, actually, where we have a graph representing what might point to what else, and then we have an assignment using a pointer that adds edges to that graph. Right? And the really fun thing we did with that, incidentally, is we did an incremental topological sort, because visiting those elements in the topological sort order optimizes convergence rate. That's not a locality optimization, but it's a good one. Okay. This is fairly breathless. Should we take a, how are we doing for time? We're about out. In that case, I will skip to my conclusions and leave you with this. My claim, and we should dispute this if you wish, is that the fundamental issue here is locality. And a big part of that is supporting composition. It's a nice quote here from a friend of mine who works for the Swiss Weather Service. Composition should not be a concern for domain scientists. We optimize components, we invite them to compose them. We should be optimizing across those components for them. And that leads you into this calculation of how to keep your metadata compact, to control the costs of not only storing it but computing on it, and to manage the amortization of that investment in optimizing for your, the locality of your sparse computation. And finally, just for fun, and this connects incidentally to the immediately previous seeding talk in some sense, if we were better at bridging the domain expertise, as we've been trying to do with our PDE tools, we might recognize that the sparsity that really makes numerical methods fast is not necessarily sparsity in the representation of the data. It's sparsity in the actual data. A lovely example of this is if you think about a galaxy full of stars, and every star is exerting gravitational force on every other star. So the force matrix is completely dense. Now we know that that force gets smaller with distance. So we do things like build a octree decomposition. Now we compute the force, which is a matrix vector product basically, right? We compute the force acting on a star by traversing that octree and asking which boxes do I need to open in order to answer that query accurately, up to some epsilon. And what we have there is an octree representation of a dense data structure. The data is all present, but each individual inner product doesn't necessarily visit it all, right? And this is data sparsity, but not necessarily representation sparsity. That kind of thing is a bridge into lots of interesting opportunities. With that, I'll finish. Thank you very much.
Well, Fred, can you go ahead and start getting set up? Well, we got the importance of locality and also the importance of compression earlier. So I'm sorry we don't have as much time for questions. It's been compressed out. But Paul, if you'd like to take one question real quick while we're switching, who do we have in the audience? Does anybody have a question they would like to ask? Matthias.
Very nice talk, and I'm curious about your opinion. So you talked a bunch about the challenges of metadata and partitioning things. Many scheduling algorithms come from the other side of saying we try to be adaptive because you will not get the metadata handled and so you will not correctly partition it anyway. So we try to compensate that by exponential decay of task sizes and many other things. So what's your take on pushing some of those problems into the scheduling algorithms?
So scheduling algorithms operate on scheduling units which have metadata about their dependence and their access times and so on. I think you're referring to tricks like, what's it called, where you...
The works dealing in a whole bunch of other schemes that try to be dynamic in the sense how they allocate work to tasks.
Right. I mean, I think you're tackling exactly the problems that I'm referring to with some statistics if you can.
Okay, that's a dissimilar.
I think.
Okay. Well, thank you very much, Paul. And